Hello, welcome to Material Science lecture. So in these lessons, we are going to continue to talk about phase diagram. So we're going to talk about binary phase diagram that involve isomorphous system. So first of all, remember that binary alloy is made up of two elements. So solidification of binary alloy, because of their limits of solubility, will form different types of alloy, as I have explained in the previous lecture. So the first one that we're going to talk about or we discuss is alloy with complete solubility limit. So this is what we call as isomorphous system. So isomorphous system refers to metal that are completely miscible in each other in both liquid states and also in solid states. So let's get started. So by the end of this lecture, you should be able to understand the isomorphous phase diagram. You should be able to understand and know how to construct and read phase diagram. And also, you should understand how, when we cool materials in non-equilibrium condition, it will cause crystal segregation in the microstructure. So just a little bit of introduction on phase diagram. I know I have talked about it in the previous lecture, but I think a lot of you are still a little bit confused what is phase diagram is all about. So a phase diagram is a map that indicates which phases are present when a substance are in equilibrium with its surrounding environment. So when we know that when we cool molten metal, to solidify them, at each temperature something will happen to that materials, to that alloy. Phase diagram can show you what phases are present in each temperature during that solidification process. So it is a map or a diagram that represents the relationship between temperature and the composition and quantity of phases at equilibrium, which will influence the microstructure of an alloy. So binary phase diagrams are helpful in predicting phase transformation and the resulting microstructure. And the simplest of these binary phase diagram is isomorphous phase diagram, which I will talk about in this video. So as I have mentioned earlier, the isomorphous system refers to metals that are completely miscible in each other in both the liquid states and also in solid states. So for example, alcohol and water is an isomorphous system. So if you have 90% of water and 10% of alcohol and you mix them together, doesn't matter at what temperature and doesn't matter at what composition of this water and alcohol, they will mix together. Even if you add up to 20% of alcohol to 30% of alcohol, they will be miscible in each other. So isomorphous system in alloy is referring to this behavior. So when you have two elements that can be mixed together, doesn't matter at what composition. So if I have 10% of alloy of metal A, 90% of metal B, if they are in this isomorphous system, they can form a single solid solution at the end of the solidification. And then when you add 80% of A, 20% of A, 80% of B, again, they will only form one solid solution. So in the end, it doesn't matter how many percentage of A and B, when you mix them together, they can be mixed with each other and form a single homogeneous solid solution. So in isomorphous system, the two components have unlimited solubility. So for this type of alloy, the resulting alloy will always form homogeneous solid solution regardless of the ratio of atoms. So when you look under the microscope, you can see different grains. So you can see grain boundaries, and you will see like what the schematic here. You have 1 grain, 2 grains, 3 grains separated with the grain boundaries. However, you cannot tell me with the isomorphous system that they are different. These grains have different phases. It's only one phase. So this is a complete solid solution. So isomorphous systems are not common, although there are a number of isomorphous systems used. And for this lecture, I will use copper-nickel system as an example. So how do we construct the phase diagram of copper-nickel? So material scientists construct it by performing experiment involving solidification of a series of copper-nickel alloy with different composition, and they construct its cooling curve. So from different experiment, they start with pure copper first. So this is how the cooling curve of pure copper will look like. As we have learned before, the solidification of pure metal involves isothermal reaction. So the solidification begins at one temperature and it ends at the same temperature. And the second experiment they did is they add a little bit percentage of nickel inside molten copper, and they construct the cooling curve. And now we will have a cooling curve of an alloy where solidification begins at one temperature and ends at different temperature. And by adding more nickel, this curve will look different again. So by adding 40% of nickel, the temperature shifts, where it begins at different temperature and ends at this temperature here. And again, they do it by adding more nickel, and they will construct a phase diagram. The temperature where it begins to solidify is here and here for a metal alloy that consists 40% of copper and 60% of nickel. And they repeat the same experiment, but now they add more nickel inside the copper. So they have 80% of nickel inside copper and 20% of copper. So now nickel is the dominant element. And the temperature where it begins to solidify is here and here. So this experiment happened with a different composition of copper and nickel. And lastly, they will construct the cooling curve of pure nickel. So again, pure metal will solidify in isothermal reaction. So it begins at one temperature and it ends at that same temperature. And as I have mentioned earlier, phase diagram represent the relationship between temperature and composition. So now to construct the phase diagram, they will plot X, in the y-axis is the temperature and in the x-axis is the composition. So in the x-axis here, this line here represent pure copper. As you move from left to right, copper composition is decreasing. And this line here represents pure nickel. And as you move from right to left, nickel composition is decreasing. From right to left, nickel composition will be decreasing. And the second step is by plotting all this temperature that they get from the cooling curve into the phase diagram. So they begin with the temperature where pure copper will solidify, and we plot that temperature into this line here. And the second step is by plotting for 20% of copper. The solidification begins at this point and it will end at this point. And they repeat the same thing with 40% of nickel. It will begin at this point here and end at this point. Repeat the same thing for the 60% of nickel. The alloy begins to solidify at that temperature and at this temperature here. And for 80% of nickel, we will have this temperature where it begins to solidify, and it will end the solidification of 80% nickel and 20% of copper at that temperature. And finally, for this line here, we will plot for the isothermal reaction of the pure nickel, and that temperature is there. And the line that connects all the point for when the solidification begins is what we call as the liquidus line. And the line that connect all the point for when the solidification ends is what we call as the solidus line. Above the liquidus line, everything will be in liquid, and below the solidus line, everything will be in solid. In between these two lines, liquid and solid will be in equilibrium. So you will have two phases in between these two lines of liquidus line and the solidus line. And as you can see, because of this isomorphous system, no matter how much copper or nickel that you have, when you mix them, even let's say you have 10% or you have 30% here, you have 50. Below liquidus line, only one type of solid will be in the microstructure because of the complete miscibility between the two elements. So you will only have one type of solid, and I will call this solid as alpha phase. So you will have homogeneous solid solution. In the microstructure, you will only have one type of grains, which is the alpha phase. So this is how the construction of the phase diagram for isomorphous system will be constructed. So how do we read phase diagram? So if let's say you have 50% of copper and 50% of nickel as your alloy. So this alloy contains half nickel and half copper. You want to use the phase diagram to understand this copper, the solidification process of this copper or the melting of this copper. You want to understand it. You want to know when will it begins to solidify or when will it begins to melt if you already have a solidified metal. So to read phase diagram, what you will need to do first is to draw that line where that represent your alloy. So if I have 50% nickel, I will draw this green line here representing my copper, my nickel composition or my copper composition. So this line represents 50% copper and 50% nickel. So above the liquidus line, this alloy will be in a complete liquid phase. And below the solidus line, this metal will be in a complete solid phase. And nuclear, if you have it in a molten state, nuclear will start to form at 1330 degrees Celsius. And crystallization will end at 1290 degrees Celsius. So this is where the solidification begins, is at that point where that alloy line, the green lines, touch the liquidus line, and the crystallization or the solidification ended where that green line touch the solidus line. So that's where it begins and ends. And this process is reversible. So when you have a already solidified alloy, you want to remelt them. So you know that using phase diagram, you will know that when it reaches 1290 degrees Celsius, my metal, solidified metal, will start to melt. And the melting process will end at 1330 degrees Celsius. So by knowing this, you know you can save energy by not using too much, by not putting it in too high temperature. You know that, okay, I will stop the furnace at 1330 degrees Celsius. This is where it will end my melting process. So in between these two lines, liquid and solid phase is in equilibrium. So if you take that and you play with it, it is like a slime. So it is a combination between liquid and also solid. So it's a gooey state. We can call it as a gooey state. So they both of these phases exist in equilibrium at that between these two lines. So that is how you read the phase diagram. So using phase diagram, we can also determine the phase composition. So let's say we have 50% copper and 50% of nickel in our alloy. So we're using the same alloy. So we want to know at 1300 degrees Celsius, what are the phases that exist at 1300 degrees Celsius for this alloy. So the way to do that is to draw the horizontal line from 1300 degrees Celsius in the y-axis, passing through this alloy line. So we are talking about that point there. So that is my alloy, that I'm the condition that I'm talking about. At 1300 degrees Celsius, what are the phases that exist at this point? So we know it lies in between this area here, between the liquidus and solidus line. So there will be two phases that exist in this at this point. So there will be liquid and there will be solid. And at this point, we want to know what is the composition of liquid. So we know that we begin with a liquid that consists 50% of copper and 50% of nickel. As the temperature starts to drop and it reaches the liquidus line, some of the liquid will start to form into solid. So the composition will now change, because some of the element will now transform into solid. So liquid, we want to know what is the composition of liquid at that point. So the way to do this is to draw this tie line here. So this tie line, you draw horizontally, passing through your liquidus and the solidus line. So for the liquid composition, you need to draw a horizontal line from the composition axis passing through the liquidus line. So here we know that our liquid at that point at 1300 degrees Celsius consists of 55.25% of copper, and the rest inside that liquid consists of 44.75% of nickel. So our liquid have this composition. And now, what is the composition of solid? So you do the same thing, you draw a vertical line from the composition line passing through the solidus line. So the composition of our solid at that point at 1300 degrees Celsius for 50% of copper and 50% of nickel alloy. At that point, we have solid phase that consists of 43.75% of copper and 56.25% of nickel. So these are the phase composition for this alloy at 1300 degrees Celsius. Now that we know how to get the phase composition, we would like to know how to determine the fraction of these phases. So we want to know, for instance, at 1300 degrees Celsius, we say we have liquid and solid with this composition. But what is the fraction of each of these phases? So we can use lever rule to determine this. So if you remember in physics, the principle of the lever. An experiment has shown that two unequal forces, when acting in opposite direction, will bring about an equilibrium when the product of the magnitude of one force and its lever arm is equal to the product of the magnitude of the other force and its lever arm. So in an alloy or a mixture of two phases, in this case solid and liquid, the lever rule stated that the mass fraction of solid phase is you can get it using this equation here, where A here is the length from the fulcrum of the lever to the liquidus line, and B is the length from the fulcrum of the lever to the solidus line. So for solid, you use the length, this length here, over the overall length times 100. So you will get the percentage of solid in that alloy at 1300 degrees Celsius. And for liquid, you will use this equation here to get the mass fraction of the liquid at 1300 degrees Celsius for this alloy. So let's do some example. Alright, so let's do the calculation for fraction, phase fraction for our copper that we're talking about. So we have copper alloy, nickel, copper nickel alloy that consists 50% of nickel and 50% of copper. So this is represented by this line here. So what does this mean? It means that when it is in solid form and in liquid form, above this liquidus line, this liquid consists of this. Below this line, this liquid consists of this. However, in between these two lines, we have liquid and solid. Some of the liquid has already been transformed into solid, and some of it still remain in liquid form. So we have two phases, and these two phases has different composition, which we already determined just then. So it has composition, liquid has composition that consists of 55.25% copper, and our solid has 43.75% of copper. So now we want to determine what are the fraction of each of these phases. So we can use lever rule to determine this. So you can draw, this is the fulcrum of your balance. So that is 50%, which is the alloy that you intend to fabricate. So you know you want we know that in the end we will have an alloy that consists 50% of copper. So that is our fulcrum, where our fulcrum will sit for our balance here, for our lever. And we know that at this point, at 1300 degrees Celsius, we have liquid and we have solid. So the composition of liquid is 55.25% of copper, and the composition of our solid is 43.75% of solid. So this is how our balance will look like. To get the mass fraction of solid, we need this distance here. So it's reverse. So that distance, the A is 5.25 and B here is 6.25. So to get the mass fraction for solid, we divided the 5.25 with the overall length, this A plus B times 100. And therefore, we will get that the mass fraction of our solid is 45.65. And for our liquid, we will get it by using the length from the solidus line to the fulcrum. And that will be 6.25 divided by the overall length times 100%. And our mass fraction for liquid is 54.35%. So always remember it is reverse. So for liquid, we use the length from the fulcrum to the liquidus line. For solid, we use the length from the fulcrum to the liquidus line. And for liquid, we use the length from the fulcrum to the solidus line. So now let's have a look. How does the microstructure form for this alloy? So this alloy consists of 50% of copper and 50% of nickel. We want to know during solidification what happened and what will be the microstructure that is formed at the end. So above the liquidus line, everything will be in liquid, as I have mentioned earlier. As soon as the temperature drops and it touches the liquidus line, some nuclei will be formed. And this composition of this nuclei, we can determine using the tie line. So using tie line, we can determine that the first nuclei that starts to form when the temperature touches the liquidus line consists of 37.5% of copper. As the temperature drops, this nuclei will start to grow. So the crystal structure will grow bigger and bigger, and the grain will become bigger and bigger. At 1300 degrees Celsius, the crystal structure, the grain will start to get bigger, and using tie line, we can determine that the solid at that stage has a composition of 43.75% of copper. And as soon as it touch or above the solidus line, what will happen is that this grain will become bigger and it will start to touch each other. So you can imagine that solid that consists of alpha solid solution will start to grow bigger and bigger, and we will touch, or they will start to impede and touch each other. Only a small amount of liquid will be left in that at that stage. So you have alpha, 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 a little bit of liquid left in that microstructure, in that alloy. And that liquid composition, you can use tie line as well to determine what is the composition of that liquid. And that liquid will have a composition around maybe, so that's maybe 60% of copper. So that is the composition of liquid, and the composition of solid at that stage is 50% of copper. And as soon as it passes that liquidus line, everything will be transformed into solid and the grain boundary will be formed. And at the end, you will have, because this is isomorphous alloy, you will have only one homogeneous phase of alpha solid solution consisting of 50% of copper and 50% of nickel. So that is how the microstructure is formed during solidification. So the solidification process that we have discussed so far from the beginning of this lecture involve equilibrium cooling, in which the cooling process happens in a much slower rate, and therefore we allow diffusions of atoms from each region when the crystal starts to form to happen. So when the nucleus starts to happen, so you can see from when we look at how the microstructures form, the nucleus has different composition than the next layer that will attach itself to that nucleus. But because it happens in much slower rate, diffusions from nucleus to the next layer can happen. We've learned this in the chapter where we learn about diffusions. So diffusions needs activation energy, it needs time for it to move within the region. So because it's much slower rate, in the end we will have a homogeneous grain. So everywhere inside the volume of that grain, we will have a composition that is homogeneous. In the end, we will have the grain that has a microstructure that has a distribution of atoms that is homogeneous in that grain. However, in reality, this is not always going to happen. What happens always is a non-equilibrium cooling. So during non-equilibrium cooling, the cooling rate is much faster. So this will stop diffusions of atoms from happening. So I will demonstrate that using this diagram here. So this schematic diagram represents the formation of microstructure of this alloy here. So this alloy consists of 55% of nickel and 45% of copper. So when non-cooling equilibrium happens, as soon as it touches this line here, nucleus will start to form. So this nucleus has a composition of 66% of nickel. And the second layer will form next to it, like around it. So we know the nucleus, and then the atoms will start to detach itself in that on that nucleus. So now remember, they have two elements. So these two elements will start to form a crystal structure around the nucleus. So the next layer, so the one with the gray, dark gray color, have a composition of 63.5%. So they are in solid now. So the 63 and inside is 66, the nucleus. If we allow equilibrium cooling, which is much faster rate, this can start to, the atoms between these two regions will start to diffuse in each other. But because cooling rate happen in a much faster rate, we stop this from happening. So the third layer at this temperature will now have 60.5, and also diffusion of atom cannot happen because of the much faster cooling rate. And then at this temperature we have the fourth layer of this layer here consists 58, and the end at this temperature, the one at the outer layer consists of 55% of nickel. So we can see that there will be a segregations of microstructure will happen. So the crystal structure will have a different composition. It has the same crystal structure. It will be FCC crystal structure. However, some region has more nickel, some region has less nickel. So we want to avoid this. So we can alter this microstructure. Even though we already have this microstructure, we can revert it back. We can do some heat treatment to make them homogeneous everywhere. Why don't we want this microstructure segregation? So logically, the nucleus will have a different microstructure, different mechanical properties compared to the other. So every region will have different mechanical properties. They now have different amount of each element inside them. So they become an isotropic. So they're not going to be the same, they're not going to be homogeneous. So you can't predict the behavior. So we want to be able, as an engineer, we want to be able to predict using any material what is going to happen to these materials when we load them. So when we have homogeneous microstructure, it is going to be easy for us to predict them. Because when we have homogeneous and isotropic, not anisotropic, isotropic microstructure, we can predict the behavior of that materials. So using heat treatment, we can revert this to become homogeneous microstructure. So this is an example of crystal segregation that happened when a monel, which is an alloy consists of nickel and copper as the main element, but they add a little bit of iron, silicon, and manganese inside it. So during rapid cooling, dendritic microstructure formed. So you can see here there's a black region and the white color region. So the lighter color region, so this is not two-phase, so this is just one phase. So this consists of alpha solid solution, but the region with the lighter color consists more copper, and the region with the darker color consists more nickel. So we have a non-homogeneous microstructure, a crystal segregation, which we want to avoid. So what can we do? So what we can do is heat treat them at 871 degrees Celsius for 12 hours. So after that, you can see that the microstructure starts to become homogenized. What happened here is atoms within regions can start to diffuse. So they can start to move around. And if we add a little bit more time at a higher temperature, you can see that the microstructure can finally become homogeneous everywhere in that volume of the grain. So that is how we can fix this problem. Alright, so before we end this lecture, let's just briefly discuss how the mechanical properties of solid isomorphous alloy are affected by its composition. So if we held the grain size constant, so for each of these composition, alloy with different composition, we assume that we have the same grain size, right? So what happened below the liquidus line, below the solidus line, only a single phase solid or single phase solid solution will exist. So we have introduced actually a component that experienced an alloy that experienced solid solution strengthening. So the mechanical behavior will change. So if you look at the tensile strength, the plot of the composition with the tensile strength here. So let's say, for example, we have this alloy with this composition here. So this alloy consists of 20% of nickel and 80% of copper. So this is 100% of copper. This line represents 100% of copper, and this represents 100% of nickel. So this alloy consists of 20% of nickel and 80% of copper. So pure copper has around 220 or something, 25 megapascal tensile strength. As we add 20% of nickel, this tensile strength has increased. So we actually introduce a strengthening mechanism that we call as solid solution strengthening. So we can alter the microstructure, we can alter the mechanical behavior by adding the second element. So that is the purpose of alloying element. So even if we look, for example, pure nickel has around 350 megapascal tensile strength. As soon as we add 20% of copper inside it, so this alloy here consists of 80% of nickel and 20% of copper. So as soon as we add 20% of copper, what will happen is that this tensile strength increase to 400 megapascal. So this is how we explain the solid solution strengthening. And again, if we look at the ductility versus the composition, so the ductility composition behavior is opposite if we compare to the tensile strength. Ductility will decrease with addition of the second component. So that ends our lecture in this video. In summary, isomorphous diagram are those for which there is a complete solubility between the elements that we add in the binary system, and in the end it will create a single solid solution. So there is a complete miscibility between the two elements. And the cooling curves are used to construct phase diagrams. So these are some of the summary that you should be able to get from this lecture. And we use tie line to determine the composition of phases, and we use lever rule to determine the phase fraction at any point in the phase diagram when we analyze a composition of alloy. So microstructure of metal can be predicted from phase diagram. So when non-equilibrium cooling are performed during solidification, we can get a crystal segregation, which are differences in the chemical composition within a grain, and we can eliminate or avoid this crystal segregation by using heat treatment or annealing process annealing. And also we've learned that the mechanical properties of alloy are dependent on its composition. So that ends our discussion today on isomorphous system. So this isomorphous system consists of elements. When we add them together, it will be completely mixed with each other. So the next lecture, we will talk about when the element that we mix will only have partial solubility limit. So that phase diagram is what we call as eutectic phase diagram. So I'll see you again in the next video. Thank you very much.